So a little bit about myself. I'm a co-founder of a company called Cache Physics. Before that, I've spent years in startups. Started my career at a company called Transmeta, which was a microprocessor company competing with Intel x86 processors. After that, I ended up at VMware, where I worked on the component of the VMware distributed system that is the brains of the system, which is that it decides where virtual machines live, how much memory they are allocated, how much compute they're allocated for the whatever SLA, SLO that the users have set up. Oops. Cache Physics, the company that my co-founder and I started about 1.5 years ago, has to do with the data path of modern cloud-native applications. And so what that means is that as soon as an application has some data needs that it makes requests for, whether they are addressed in some in-memory component or down the operating system or down a file system path onto disks or to flash, that entire path, the data path, we found that working with a lot of customers that data path had a lot of problems, a lot of lack of visibility, lack of observability, and lack of control. And that was causing a lot of problems for modern applications from the point of view of managing their performance and managing their latency. So we're all about the real-time predictive modeling of data access patterns and then using those to increase the performance and cost efficiency of in-memory computing. Okay? And that'll become clear. So the background for this is that in-memory computation is actually really hard to operationalize, right? App data requirements change constantly. A classic example I give is that if you're a developer at, let's say, a car rental company or a ride-sharing company, right? Let's just say that this morning I arrived at this conference using a ride-sharing app, right? If you're a developer, just imagine that you're the developer. Your product manager comes up to you and says, last week I asked you to implement a piece of code that anytime somebody opens up that ride-sharing app, that piece of code goes and accesses the last 4 records for that user's rides, okay? But that's last week. This week, I want you to go and look at the last 5. Now, you go into your code, and what do? 1 character change in your code, right? And you just check it in. It goes to production. Unbeknownst to you, underneath the surface, you have now increased the load on your entire data path by what? 25%. 1 character change, 25% code. 25% increase in the working set, 25% increase in the data throughput needs, the DB needs, the memory needs, right? Do you guys buy that as a toy argument here? So that's the sort of thing we started to see working with customers, right? So app data needs are changing constantly, and so doing what we've always done, which is some sort of a notion of quality of service. When a user opens up an app, or a user logs into a website, or a user logs in and tries to check their email, we have these concepts of, well, there has to be some quality of service. This request should not take more than a second. That one should not take more than 10 milliseconds, etc. Right? Well, that becomes really, really hard, because the app data needs are constantly changing. The higher velocity in the development teams creates problems for the entire path that are very hard to understand and model. So that's one thing that should be seen as background here. Another one is that the data path itself, the hardware part, has become more complex and more layered. And this is really the hardware industry's way of dealing with the problem of the physics of latency. Right? So several of these layers are new in the last few years. Right? So of course you have the processor level instruction cache, data cache, last level caches, right? And then you've got DRAM. And so of course a lot of us have putting in massive amounts of data sets in DRAM. Some of them don't fit there. So now there's new tiers like 3 crosspoint and magnetic memory and resistive memory that are being introduced. And then we used to have a very simple thing called flash. Now that's even complicated, because now you've got fast flash, and then you've got slow flash, and you've got a capacity flash, right? Of course, then you have hard drives, and then the slow hard drives, and then the really, really, really slow hard drives, right? So with large data sets, in your particular application or your infrastructure, it might not be that you're using all of these today. You might be using some subset of them, but this is the options available. This is the complexity that is actually real in terms of choices that you have to make. So the problem of data management and across these tiers for the purposes of performance is getting much harder, even though we're getting better choices, right? We're getting more choices, but the problem of choice, right, is much more complex than before. So that's the second piece that we need to keep in mind with respect to the complexities of in-memory computing from the memory and the data side. Okay, so data path performance is critical. So you have a user logs in, some DB gets hit, right? Or maybe it's a key value store that gets hit, right? Well, now you've got this whole distributed platform that is running on top of. At the end of the day, you're going to hit servers that have DRAM. You're going to hit CPUs that have caches. Or you're going to hit some other intermediary layer, persistent memory, and so on. Maybe you go across a network, and there's some centralized storage or an object storage that's across the network, right? So all of these, every single component in this has DRAM and has some ways that we monitor that stuff. So the example little dashboard snippet that I put up here is a performance dashboard that shows you maybe some cache hit ratio for the cache for that, and it shows you the current latency for some percentile, right? So this is our state of the art in terms of the observability of the data paths today, right? For each of those layers. So despite the fact that data path performance is critical, our ability to manage it and observe it is actually like pretty non-existent. So if I was to ask you all a question, actually a pretty simple question, top right, is the performance in this made up example of 65% cache hit ratio and 16.7 milliseconds of 99.5th percentile latency, is that good or not? So I think if this was your application, you'd actually kind of have to think about that. Because the real purpose of asking that question is, can it be improved? Can that be improved, or should I be looking somewhere else in my stack to try to improve my overall latency? Right? Other questions that should be easy to ask are actually very hard to answer. How much DRAM versus flash for this particular analytics job? And how should I set up my tiers? How much of this workload I need to put in actual DRAM, and how much of it I can just fault in, right? It's hard to answer that question in a way that would survive application level changes or workload changes, right? How do I achieve a certain percentile of latency, and so on, okay? So despite the fact that we all care deeply about data path performance, right, our tools to actually do something about it, right, are fairly limited today. Okay, so of course, as you'd expect, algorithms to the rescue. So we're going to try to see in the next few slides, I'm going to go pretty technical. I'm not sure if it's something you're used to for a conference like this, but we're going to go actually very, very technical, because what we're going to try to do is to figure out a way to solve this problem once and for all. Okay, so we're going to go a little bit more generic. We're going to try to do it algorithmically rather than heuristics and rather than finger in the air sort of stuff, right? Estimations, etc. We'll try to algorithmically solve this problem. Okay, so on the left-hand side is a dashboard snippet that we started with, right? On the right-hand side is what I want to get to. I want to get to the ability of being able to plot what the latency of any data path is going to be, okay, given how much memory I allocate. Okay, so today you can translate the left-hand side to the right-hand side by drawing a single dot. Okay, because you're observing it, right? The dot moves, of course, throughout the course of the day, right? The latency you achieve, notice that the y-axis is latency here, and the x-axis is total amount of memory allocated. So the dot will move, okay, but you know where the dot is at any instant in time for your application. So our objective, the reason why this is a very technical talk, is to do something a little bit different. What we want to do is to learn the performance model of the application that is sending the data requests and the memory subsystems, the DB, the disk, etc. We want to learn those models. Okay? And the result of those models actually is going to be a simple curve. So notice this curve. Again, x-axis is memory, y-axis is latency. What it's saying is that if you were to reduce the amount of memory allocated to this application, latency would get worse. We normally expect that, right? Less memory, bad latency. If you add memory to this workload, what will happen, right? So by the way, this picture is actually a real customer production workload, which we will actually look at in a bit more detail. Okay, so let's do that, right? So if we're going to algorithmically solve this problem once and for all so that you can take a tool which will see the traffic going from an application to its data path and then be able to just model it automatically and give you answers, right? We need to understand what this curve is all about. So the same model as before. X-axis is still memory size, y-axis is latency. And now we're saying, okay, well, let's say that currently you are operating a 10 gigabyte memory for this workload. Okay, so it's a small toy workload for us to play with, right? So it's 10 gigabytes because the dot is sitting at about 10 gigabytes. If I'm right, let's say, well, yeah, about 10 gigabytes, right? And currently it's achieving 2.5 milliseconds of latency. Let's just say, okay? So now you're doing this performance optimization, and somebody comes to you and says, look, I need to get lower latency in this particular path. This is too high. Right? So you might, for example, say, okay, I'm going to double this memory. And you go ahead and double it. Do we get a performance improvement? Show of hands. In this case, do we get, no, we don't get a performance. Thank you for breaking the ice with audience participation here. Hopefully it's contagious. So we don't get a performance improvement here. Right, it's clear because we know this curve, but let's say you actually tested this in production. Now, you're very insistent and you're going to double the memory again. Now we're at 4x where we started. Do we get a performance improvement? No. We get 8x now. If you're spending $1,000 a day on this application, let's just say, right? Now you're at $8,000 a day. We still don't get a performance improvement. Now, maybe you'll give up. Maybe you'll keep going. But if you give up, you would have been right at the precipice of a performance improvement regime that will last all the way out to whatever your performance requirements were. But you may not know that if you don't know this curve. You see, so by knowing this curve, we can make better decisions about how to size, how to manage the memory that our application is using. I admit it's a little bit abstract, but these are real actual workloads with real analysis. Now, there's kind of two ways to determine this curve, right? So what this gentleman up here in the thought experiment we were running was doing was, well, he was continuing to add more memory or to reduce memory and kind of interactively explore this curve, right? Ideally, we don't want to do that because we don't want to make any change in production unless we know what the result is. Okay. So what we want to do is we want to determine this curve without changes in production. We want to do a what-if real-time analysis of that workload and say, hey, give me all of the points on this curve without me interactively messing up and taking risk in production. Does that make sense? Okay, that's the basis for the next several slides. I just want to make sure we go over it. One more thing I want to ask is, why is it that this curve is not always monotonically decreasing? Why isn't it that for every gigabyte of memory that I add to this workload, the performance doesn't improve? Why are there flat regions at all? Any thoughts? Why might it be?
It depends on the application, how it's encoded, right? And whether they're even utilizing the extra memory, right? So
yeah.
Applications are not ready to.
Thank you. So for the recording, the one suggestion was, hey, this really depends upon how the application's code is written, right? And the one example that you provided was, well, maybe the application is not really able to use more memory, right? And actually, that's a really good example because what would happen is that then it would be flat to infinity, right? So that's a really actually kind of a base case example of a curve that's just flat to infinity, right? It gets some benefits and then flat to infinity because there's no improvement of latency you can get by adding more memory. Make sense? There are actually more nuanced ones because in this case, it wasn't flat to infinity, at least in the first few cliffs here.
Could you describe the whole system? I came in the middle.
The whole system is actually very simple. The amount of memory allocated to a single application, right, versus the latency that it achieves.
But I mean, you took about I/O, you took out anything.
Well, I mean, I drew a picture earlier, which I kind of abstracting over. That's okay, but the general idea is you need memory to achieve speed ups. Could be in cache, it could be in some working set.
Sometimes it helps and sometimes it doesn't. I think
Exactly. Yes, exactly. Sometimes it helps and sometimes it does. But sometimes it helps but you have to get over a hump. Like in this case, we had to go from $1,000 to $8,000 before any improvement happened, right? Well, why was that? It has to do with the working set, right? Like, okay, let's just go back to the simplest example. Let's say you have an inner loop and an outer loop. We're not talking about gigabytes, you're just talking about kilobytes or something, right? So there's some amount of data that you're accessing in the inner loop, right, that's constantly accessed, and then you exit the inner loop and you come to the outer loop, and there's some data that you access, right? So in that case, you would see kind of a flat region and a drop, and a flat region and a drop, simply because there's a working set, right? If you don't fit the working set of that part of the workload, that loop, let's say, right, you're going to thrash. So anytime you see a flat region here, in your mind, you should just think it's thrashing. It's just I can't fit enough stuff into that tier to be able to operate on it efficiently, and so performance is going to suck. It's not going to improve much by adding memory until I can fit that working set into memory, and boom, I have a performance improvement. Okay, does that make sense? Okay, so these curves, these performance utility curves, memory utility curves, right? Plotting the final result that we want, which is low latency on the y-axis, memory size or dollar investment on the x-axis. They are going to illustrate for us how we should size our application for any given tier. Okay? So let's take another example. Let's say that, look, for this particular application, you just want efficiency. Like maybe it's a batch workload, right? We do a lot of batch workload in the community. Actually, perhaps much of data computing today is still not streaming, and it's kind of batch oriented, right? And so perhaps what you care about is efficiency. Then we're going to go back to the same curve, and we're going to say, can we algorithmically find the most efficient operating points for this application, for that whatever working workload that application is actually encountering in real production over time, right? So what we did is we just mathematically and visually, it's very easy actually, where do you want to operate on those curves? You don't want to operate on a flat region, because that means you put money at stake for no improvement. So you want to find the points on these curves, on these models, that have the biggest slope gradient, basically, right? So it's going to be at the bottom of the cliffs. Every time you see a cliff, you operate at the bottom of the cliff. That's the most efficient operating point. So depending upon your goal for what it is that you're trying to accomplish for your application, for your infrastructure, right, you can read different things from this curve. So far, so good? Okay. So here, let's have some fun. So now that we understand these curves, and again, if you came late, just all you have to think about is dollar signs on the x-axis, and then latency, or let's just say latency on the y-axis. So lower is better, always on the y-axis. Okay. So the fun we're going to have is we're going to look at some anonymized customer workloads. So you see a bunch of things like coded like T00 all the way to T29. Right? These are real customer workloads that we've been helping them with and analyzing to help them size their environments. And the main thing to take away here is the diversity, right? So for example, this is a very small working set. Within 18 gigabytes, you've achieved the best performance you can. But you notice how steep those curves are, right? All of the benefit was actually found in the first few gigabytes. Small, real customer workload. Now let's get a little bigger. This particular example is about 500 gigabytes of memory needed to achieve all of the performance benefits. But you see these cliffs, right? And the cliff in this case, depending upon which system you're running, depends upon which in-memory computing system you're running, and you see a couple different examples here, that you have cliffs all the way out to about 500 gigabytes. Right? So in that case, in the green line that you see for T19, which is highlighted there, you'll see that most of your benefit comes right at the end. You really got it. It's a huge working set. If you don't fit it, you don't get the benefit. The cliff is all the way at the end. Okay? And then another example is this 600 gigabyte working set, which is T08, highlighted here, where again, depending upon which system you're running, right, you got to go all the way out to the end to be able to get the benefit. Okay? All right. So jump in if you have comments. Now, so far we've looked at those curves. We've talked about like what would we do with them if you had them. If you had them for your application, for your infrastructure, what would you do with it, right? We've talked about a couple of those. The interesting thing here is that they're not static. They actually move. Now, why would that model move? Why would the behavior of the application change? Well, some workloads are higher velocity, and some workloads are not high velocity. So an example of a workload that may not change is the same batch job running every couple of hours. Well, the behavior of the application is not going to change that much. But if you're dealing with an internet service that has some database to access, well, that might change because different items were on sale that weekend or something like that, right? Or more people were looking for rides on a ride-sharing app at a certain time, right? So what I'm going to show you here is, now this is very highly sped up, just so you know. On the left-hand side is a very high velocity workload. There's a few things going on here. So first, again, in this case, this is a cache system, so it's in memory, but it's used as a cache. And the workload is that curve that, as you're already used to on the left-hand side, but it's changing, right? Now, as this changes, you also start to see the green line, which is this vertical line, okay? And that vertical line is the amount of allocated memory needed in this in-memory compute system to achieve the SLA set by the user, the operator, or the developer, right? So the SLO in this case is 50% in terms of miss ratios because this is a cache system. So you'll see the green is moving because the system doesn't want to get worse than 0.5. Okay? But you also see this purple line which bounces because it's looking for that efficiency with the one constraint, find the most efficient point that does not violate the SLO. Okay? So now this is our system. Now you see this spike in workload, right? All of a sudden there's an unexpected spike in the workload and the entire curve just goes off the chart, right? So all of our buffers that our system recommended to this customer just went off the chart, right? Because you needed a lot more memory to be able to accommodate the workload, right? Now without our system, without modeling, real-time modeling of this curve, the customer would not have been able to react and understand what to do because of this new pattern of traffic, right? Now that pattern subsides and then our system identifies, hey, everything's okay now. You still operate at the purple. We'll give you enough buffer in front of the green vertical line so that you still won't violate your SLA. But if you want to become more efficient now that the storm has subsided from the workload, right, that you can do that. Does that make sense? Okay. All right. Now, the one on the right-hand side, just for reference, is actually not that high velocity of workload. So here you have, the system is still operating the way it does. You still got the green line and you got the purple line, but you see the purple line is just really, really solid, right? Because it's giving you lots of headroom for changes to happen and you still won't have a performance problem that will occur from that, right? So again, just two different workloads with different velocities and just once again, right, these are highly sped up. In these two cases, right, these events that you saw here were happening over hours and days, basically. Okay? All right. Okay, so now we've seen how these curves can be used for fairly kind of easy things. Now let's get more advanced and have even more fun. So this time, a few differences. So you'll see on the y-axis this time I've plotted the 95th percentile latency. In the past, it was just average latency, right? In this case, we went all the way to 95th percentile. And of course, you can go to 99.5, whatever your SLA might be. Right? The x-axis is still memory size. But this time, our product team or our business team came in and said, look, I don't just want efficiency, and I don't just want really good latency. That's not good enough for this particular app. Right? I actually want an SLO. I don't want the latency to ever be worse than 7 milliseconds. Okay? So how would we implement that, right? So the way that it's actually pretty simple, right? You already have latency on the y-axis. You would go and find 7 milliseconds, which in this case is the example that I'm providing. And then you would go and find out, well, what is my memory allocation needed to never miss that? Okay, and you'd build some buffer, and that buffer in this case would be about 18 gigabytes because you're going to operate at the bottom of the very last cliff on the right-hand side that you notice there. Right? So now what we've done is we've taken this real-time model and we've adapted it so that for this admittedly OLTP-oriented workload, that you can always make sure that you don't hit you don't have a miss in your latency SLOs. Okay. So this, by the way, is the world's first data path latency guarantee system here. And again, the reason why this is even possible is that we know the shape of the model. We can predict what will happen. And until this capability, we were not able to do that, right? So the only way before this to get SLAs was to have your entire working set in DRAM. It's the only way, right? Because you had to throw hardware at the problem. And that, of course, you can do that for a large type of workloads, but you can't do that for everything in the world. And so anytime you couldn't afford to put everything in DRAM, or it hurt your bottom line or hurt your margins for your business to force everything into DRAM, right? Other than that, you had no guarantee on latency. You had no SLA capability, right? Because you just couldn't understand or predict what the workload was going to do in its actual data path behavior. Okay, so it's kind of a binary thing. Either you get SLAs by putting everything in memory, or you had no SLA, right? And now we've got this ability to say, hey, you just specify your SLA, and we'll help you figure out whether this workload needs to be 100% DRAM or can be 90% DRAM or could be 1% DRAM, right? Really depending upon your actual workload access and pattern. So now you get the rest, instead of it being a binary decision, right? No SLA or all DRAM. Now every other point in that spectrum becomes available to you as an allocation strategy. Okay, so another thing we talked about earlier was memory thrashing, right? So what's the definition of memory thrashing? The definition is actually very simple. It was first defined in the 1960s. It's simply that when you go and try to get a piece of data and bring it into DRAM so that you can operate on it, that it's not there, which is okay because not all data is always going to be DRAM. But by the time that you need that piece of data again, it's not there anymore because something else pushed it out. Right? So somehow something about that workload keeps pushing stuff out before you can use it. Right? If it was still in DRAM, you'd be able to use it and your performance would be beautiful. But it always gets pushed out. Right? So that's the kind of the practical working definition of thrashing. And as we already know, that in any of these curves that we've looked at, the thrashing is very easy to spot because it's going to be those flat regions. Right? You didn't fit the working set, and so you're thrashing. Now, as soon as you fit the working set into DRAM, right, thrashing goes away, and then you get a precipitous improvement in performance with these curves showing what that prediction is going to be. So what we said was, okay, so far so good. We know how to control latency. We know how to build SLOs on top of it. We know how to improve efficiency. We know how to run our system at the most efficient operating points. But these like thrashing things, we can't really do anything about that because that's inherent in the workload. Like, how do we go and give somehow better than what the thrashing is doing, which is those flat regions? So this was actually very, very exciting development, very recent. And I'm happy to discuss this with you because what we found is that there actually exist ways that you can actually cut that thrashing out completely and get this free performance benefit. Okay. Now this is very weird, right? Because again, like one would assume that thrashing is just thrashing. If you can't fit the working set, you can't fit it. Like, how can you get better than that, right? It should be impossible. Well, it turns out that if you can draw these curves, in this case, the drawing of the curve is a black curve, which is that real-time performance modeling capability, you can tweak the cache algorithm underneath to know that thrashing is going on and to remediate against it. Okay, so we set about implementing that, and there's several academic papers and a best paper award last year that this technology received at the world's #1 systems conference on that particular invention. So what we set out to do was to say, hey, can we teach the system underneath, right, to detect that there is a thrashing going on and actually do something about it in a way that's actually repeatable, works for every workload, and is predictable. And that's what the red line is. So in this case, the red line, which is a slightly tweaked cache system underneath, was able to detect that the thrashing was going on, which is what the black curve told it, and then dynamically adapt so that the thrashing was removed. And so in this case, so in terms of performance benefits and pure performance improvements there, the left-hand side is the best across hundreds of different customer workloads that we've tested this against, which is 69% of the optimal, and 38% is kind of a little bit more typical of the performance improvement. Right? Again, remember, this is free. There's no cost to it other than tweaking your cache algorithm underneath to become intelligent. Right? So this is a roadmap item for us, and we're looking for customers to prototype this in grid gain, Redis, Memcache, in large memory environments. Okay? So we would love to work with you on implementing this in your system. Again, just as long as you can draw the black curve, the red curve is predictable and it's free. Okay. Now, another use case of this is multi-tier sizing. This is often overlooked, so I wanted to emphasize it, right? Because again, unless you are going to be completely 100% DRAM for every single workload in your environment, which is rare, typically we only have a small percentage of those, right? You have this problem that you have to deal with, which is, how much of my overall budget, my compute budget, my data budget goes to DRAM versus flash versus local remote network, and so on, right? So again, the same type of model, just tweaked a little bit differently, allows us to be able to figure out what the performance of the entire system end to end is going to be, okay, with different budgets at different layers. Right, so imagine just these being sliders. Right, you just go and slide and look at the performance prediction depending upon your capacity planning target for what the cost versus the benefits that you're looking for end-to-end data path latency. Okay. So the final use case, and there's many more, but and they get kind of more nitty-gritty, but at the high level, the final use case I want to talk about is per app memory pools. And so the general concept here is so far we've talked about single app at a time, but that's not typical, right? It's not typical to have your infrastructure that isolated. Oftentimes you actually have interference. You have big pool of memory, and you have to decide how much of that big pool of memory, you got 100 servers or thousands or tens of thousands of servers, whatever it is that you have, or even in a single machine running containers, you still have to decide how much of the resources are allocated to which app, which process, which container, which distributed system. Right? So when you have pools, you have a decision to make on how much of each resource goes to each client, each app. Right? And so now what we can do is, rather than thinking about the pool as a single whole and doing our modeling there, instead we just do our models on a per app basis and then compare and then provide recommendations. Right? So in this case, what you see is the colored rectangle is the overall size abstracted of the overall pool. Each client is being modeled separately, and then a very simple algorithm that we have on top compares the performance benefits versus the cost versus the SLA of each app, and then defines how much of the overall pool should go to that app so that the SLA is not missed, the cost is reduced, as well as there's enough buffer allowed. Right? So this was the final use case that I wanted to talk about. All of this, of course, is based on this concept of saying, hey, if we don't know what our workloads are doing, how can we make good allocation decisions? So let's spend the energy to nip that problem in its butt and really understand and model and predict what the workload's needs are in terms of memory and other resources in the system, and then adapt to it. Okay. So this is kind of an observability dashboard, the kind of the first use case that we talked about, which is sizing and capacity planning, right? So here, for different workloads in that memory pool, right, they're operating differently and have different behaviors, and for each one of them, right, there's latency targets, there's the current operating points, and then remediation suggestions for how to change the system, either to save money, whichever goal you have, right? So think of that as the entry point into the world of managing your memory resources and your data path resources. Okay, so architecturally what that looks like is you keep your existing applications as is on the left-hand side, right? You don't have to go and change a framework. If you're using Java, please keep Java, okay? If you're using a certain application performance monitoring system, you keep that, right? So our concept is we pull as much as possible information from open source tooling or existing interfaces to understand the traffic. And then you get to keep your existing infrastructure. We're not going to come in and say, hey, to get this benefit, you have to change how you do in-memory computing, how you do in-memory caching, or whether you use MySQL versus Postgres. We're not going to do that, right? So really, what we are is a system on the side, a system of intelligence that operates in parallel to the operations of your application, where we're getting this highly sampled access pattern of the way that your application accesses data. It goes into our system, where we do this performance modeling real time as well as over the long run to understand the access patterns of your workloads into your in-memory compute, and then use those to predict and to control. So you'll get API callbacks or these dashboards, an example that I showed you, where you can, again, choose your target, either enforce an SLA or to optimize for cost or other factors, or allow your developers to directly access your monitoring dashboard so they can optimize their application themselves, right? So this model predict control loop sitting as a system of intelligence alongside your application. Okay, so I wanted to leave a little bit of time for questions. So here's some takeaways and some asks, right? So what we talked about today is a fundamental technology breakthrough for in-memory computing. The algorithms underneath the surface that are making this possible are kind of like a once-in-a-lifetime sort of thing for people who work on memory systems. The last time a breakthrough like this happened for memory management was in 1971, coming out of IBM, IBM Almaden back then. And so what this allows us to do is to get optimal cost for the same performance, right? So you get these knobs, you get these levers, right? You can optimize cost, fix SLA, and keep performance the same. So it gives you those types of tools. The world's first latency SLO system on the data path, and really empowering a self-tuning data path. So the asks are, we're looking for new customer projects. We're a Silicon Valley venture-funded startup. And we have 2 guarantees that we can give you. You get to pick one, right? Working with you as a customer. The first is we'll give you a 50%, we'll enable a 50% efficiency gain, and that's a guarantee. If we don't do that, you don't pay us, or we give you money back. Okay? And that's how confident we are that people are not sizing their environments correctly because they don't have the ability to get this like X-ray vision into the actual problems in the environment in the data path, right? Or we'll give you a latency SLO guarantee, which is if you tie your system and you size your system in as much as the past predicts the future, and you size it based on our recommendations, that your latency SLOs will be met. If not, you get your money back. Okay. And so the application for this, of course, for this conference is on in-memory computing, and we do more than that, but that's what we're talking about here. So if you have a database that gets accesses from applications written in any language, or a key value store, or even a file system, operating system level, disk subsystem I/O latency problems that you want to see solved, would love to work with you. And there's 2 of us here. Vikas is in the back, who's my co-founder and our CTO working, and would love to talk to you. So thank you very much for your time and bearing with me through kind of some pretty technical depth, but I deliberately kind of ended a little early so that we'd have the chance to discuss and ask questions, please. Why don't you go first?
First of all, at least thank you.
Okay. You're welcome.
So 2 questions. First, I think you posed a problem initially saying that you don't need to have a lot of data. Remember, it's like you would do it through trial and error, but then from what the model looks like, as if you are actually gathering a lot of application empirical data to actually predict the curves. So I'm just trying to understand where.
Okay, yeah, that's a very good question. So let me repeat it for the recording, which is that earlier we had hinted that you don't need a lot of data to come up with these models. Like the algorithm doesn't need a lot of data to come up with these models, but we didn't really clarify that. So you're absolutely right. We didn't go into that detail. So the way the system works, and in the architecture diagram, I'd shown you kind of this instrumentation path that goes into our microservice, which is doing the modeling. So it's all dependent upon sampling. So we've invented a new way of sampling the traffic that goes from an app to wherever it's getting its data from in all the tiers, right? Such that we can operate at 0.1% sampling and still be 99% accurate. Okay. So the modeling that's going on underneath the surface is all about this Thrash business, right? Like if you use a piece of data, how long before you need it again? And so therefore, how big does your cache have to be so that that data will still be there when you need it? Typically, that sort of an algorithm it couldn't be done with any sampling at all, right? All the prior work was you got to look at every single data point, and you have to model it for every single cache size. And so people who try to do that sort of optimization would take a day's worth of workload trace, and it would take them a week to run it. And by that time, the workload has changed. So that's why this feels so new. The idea of optimizing this way has been around for 40 years, but it was not possible because by the time you would do the analysis, the workload has changed. I mean, it takes you 5 times longer to run the analysis than the time that it took to collect the data. So the innovation for us was to come up with a new invention around how to do that sampling so that you can keep your accuracy high and actually keep up in real time, with very low CPU cost, very small, megabytes of memory needed to model terabytes of caches, terabytes of flash, terabytes of petabytes of disk accesses, right? So the summary for the answer to your question is the magic is in the sampling, and it's 0.1% sampling. So think about 1,000 requests go by, and we only sniff one of them to build our models. Yeah. Can I? Yeah.
I was going to add, in addition to that, so are you saying that by just sampling a little bit that you can develop this model?
Yes.
But even without knowing, I mean, if you're always So if you're functioning at the, at the initial level.
Yes.
How do you know that, by going much further out that you'll get that big of a.
Right. So the question is, if you're operating on the screen right now, we see a gray dot.
Right.
If you're currently operating at the gray dot, how can the algorithm possibly know what the performance would be if you went to 20x the cache size, right? How would that happen, right? So the way to think about this is that we're not looking at whether something was available at any tier of memory, hit in the cache, hit in the flash, hit somewhere else on the network. We're not looking at that. We're looking at what the application's needs were, what it was requesting. We couldn't care less what any particular tier did right now, because what we want to do is we want to model all possible sizes, so we cannot be influenced or biased by the current size. We cannot be influenced or biased by the current parameters. Right? All these cache systems have multiple parameters, as you're familiar with, right? We model all of those simultaneously because we don't want to be biased by the current one. So we always collect our instrumentation before you get a cache hit or miss, right at the top there, before the hit or miss, right? And then, as a result, if a piece of data would have been a hit, you had a bigger cache, we would know because our model would actually be able to see that. Right? That is the piece that used to require 5x longer than in real time to model, and that's what we made real time. Okay? Think of it as just reuse modeling, but reuse modeling is very, very expensive from a memory perspective.
For that graph and some of the graphs that you have shown earlier,
Yes.
are they based on predictions or actual measurements of the real memories cache sizes? Let's say,
So we've done both. So in this plot here, anytime you see a dotted line, that's our approximation. And the solid lines are the real thing, running on its own at different memory sizes, and then us comparing against them. So you see the dotted lines are always almost right on top of the solid line. Right? So the solid line is measured, dotted line was our prediction.
the solid line, so for example, you look at the one on the bottom left.
So the solid line, so for example, if you look at any green curve, there you see the dotted and the solid underneath it. Right? So dotted is our prediction, and the solid underneath it, right under it, was the actual. So you can see the dotted is right on top, right?
So what you're saying is the solid is if you do, instead of just the sampling, you did actually capture the whole set.
We capture the whole set. Ran the simulation for hundreds of different cache sizes to draw the solid line, and then we said, look, how good did we do? And that's what the dotted line is. So you can see, I mean, it's deceptive because they're right on top of each other. They look like one curve. They're not actually. There's two curves. On each of these, you see 3 lines because actually there's 6. It's just that they're always on top of each other, and so it's very hard to see. Did I answer the question?
Yeah, partially, but then, if you sample only, you said like, I think like 1%.
0.1%.
0.1, then how is that sufficient?
So the question is, if I'm only sampling 0.1%, how can I possibly get this high in accuracy out hundreds of gigabytes or terabytes? And the answer is the statistical, it's statistical mechanics underneath. But the way to think about this is, when Gallup or NBC or CBS want to do a poll of the general population's behaviors, they only call 1,000 to 1,500 people around the country, and then the statisticians sit down and figure out how to project from there to what the whole population will do. And what we're doing is the moral equivalent of that, and that's the fundamental reason why this works. Okay, so we don't have to look at all of the keys and the values that are going through the system. If we pick carefully which ones we sample, and that's what Gallup does when they pick up the phone, they have to very carefully pick who they talk to get an opinion, and then if you do that carefully, you can now project to the whole population with good accuracy.
Right, but that example works because it requires, the domain knowledge of, selecting a sample population that is representative of the entire population, right? So that implies here for the prediction, the sampling needs to know, subcapital domain knowledge of
So
the location
Yes. So the Gallup doesn't do domain-oriented sampling. They do either random sampling or stratified random sampling. And so what we're doing is spatially random sampling, which is the moral equivalent. That's our invention of how to get all the statistics results to actually apply in this domain. We couldn't just do random sampling. We had to invent a new style of sampling that's called spatially random sampling. And then all of the results that Gallup and CBS and every other statistician in the world uses work now because we have a sampling regime that doesn't need to be domain specific. Okay, very good question actually. In the back there?
Any thoughts about bringing this to processor cache level?
So the question was, any thought about bringing this to the processor cache level? Thoughts, yes, lots of thoughts. Up until recently, Intel's processors did not have the ability to allocate the last level cache per process in a dynamic partitioning mechanism. They've just introduced that into the Intel Xeon. And so we are looking for customers to go and work with on that project. Okay, let's talk. That feature just went into the latest processor. So yeah, we believe with the same techniques apply. We just want to work with some real data sets there. There's one more question.
I'll ask my second question.
So your second question. So we're going to disband pretty soon. So we're going to be around the rest of the day. We would love to. No obligations. You don't have to buy from me. I just want to get to meet you and to get to talk and find use cases and problems. So there's no sales call, but I'd love to meet you afterwards. Please go ahead.
I was just saying on the implementation side of things, when you
Yes.
close the loop, assuming you have recommendations to move cache around,
Yes.
you're probably making assumptions about the elasticity on the app side itself, right? That
Yes.
they could spin up, let's say, extra instances. Because oftentimes,
Sure.
let's say in a Java stack,
Yes.
your heap sizes would be defined a priori, right?
Yes.
And it's not easy to change them in runtime unless you actually take down the service and bring it up again. So I'm just curious, in your experience with your customers, what have you seen?
So we've seen a couple of things. One, for application level caching at the network layer, so Redis, Memcache, GridGain, where GridGain in the network deployment sort of case, and then people trying to do data-oriented computation where they're trying to bring a certain amount of data into DRAM, let's say in the compute line, right? Those cases, right? This is a no-brainer. It's very, very simple to see how this would work, right? Because you're dealing with allocation across a network, which means you're almost by definition flexible on
Sure.
You have a proxy in the middle, you've got a router in the middle. It's trivial to just go add and remove, right? So that's been a good set of experiences with us. On a single node, you have a slightly different challenge, right? Like you mentioned, right? So in a monolithic app where you've got a Java heap and then you're doing a lot of computation in Java heap, what we would do is we should just run this for a week. Right? Just run this for a week for whatever the pattern that your application has, and at the end of the week, if you need to make a change, you make a change, and then you run it for another week. Right? So not every workload is such high velocity that you need to adjust per minute or per hour, right? But workload patterns change, right? Even the slow-moving ones, they change because the application changes. The developer checks in on one character change and now it changes, right? Or a usage pattern changes. So again, it's really dependent upon what you're doing, but at the end of the day, the bottom line is every workload needs memory, and if we don't know how much it needs, how are we
At least
what
you
are we
start somewhere, right?
Yes, right.
So when you're assessing,
Can I take this?
Sorry.
Yes, please.
Yeah.
I'm very new to this, especially in memory management.
Yes.
So I'll try to explain my problem. You can tell me
Yes.
about this is a solution. So we have lots of data that we populate to Redis as a storage because it's much faster than our in-memory representation of the data because we can't keep expanding the memory as much as we want to.
Right.
We did not think of Flash or DRAM or
Right.
anything. So and it's a Java stack. So we thought Redis would be easier, and then we have a way of supplying Redis data to several app servers, maybe 25, 26, what have you. But we find that after a certain point in time, it doesn't really serve its purpose. We find issues, we have timeouts on our app layer.
Right.
So it looks like it's a classic case where any of these solutions might help, but what would your take be on this?
Well, at the highest level, right, the first stage in diagnosing a problem where you have some shared pool, it feels like there's lots of application servers that are hitting your Redis, right?
Yes.
So it's a shared pool. So the first thing I would be looking at would be, hey, what tools can we get you that will help you understand the usage patterns of each of those 25 application servers that are hitting your shared cache? Because it's quite possible that what's happening is that there is one or two of those that is behaving in a way that's thrashing the others because it's a shared pool, right? So that's the first place I would start to go and debug that, right? And then if that is a problem, then you're going to come up with some way, as I showed earlier, to isolate each tenant or each of those app servers so that it's interfering less with others. So that can be one sketch. What ideally what we want to do is we're going to give you the visibility tool so that when you have a problem like that, you can go in and say, oh, okay, this must be the culprit. Let me try and predict what would happen if I change something in those tiers. Right? Now, in the longer run, what we want to do there is give you SLAs for that. So that as soon as that starts to happen, you get an email from us or an alert from us long before your users see that, because we'll see the workload pattern shift. We will be the first tool to see that. Right, because we see, oh, this is odd, like this curve shifted long before timeouts happen, right? So we want to now send that to you and then give a recommendation with it. Yeah, but I think it requires a little bit more deeper conversation. There may be something we could do here to help you. Thank you.
In our environment, we're looking at a machine learning, deep learning environment where we're putting out different models, changing them over time. I want a shared infrastructure with many requests coming in to get an inference and get a result back. I want to introduce a new model to the environment. I can't emulate the production environment. I can do A/B testing. I can't emulate the production environment at full volume.
Yeah.
Is there a way that we could use your engine to look at what the current environment is doing and look at a test environment that's just running the new model and assess the impact it's going to have and what changes are needed?
The answer to that is yes, but it requires a little bit of this is kind of a fairly automatable solution. That requires a little bit more help, because what we would be looking to do there is, the sampling regime that we do so that we can run these like off to the side simulations that give us all this accuracy, but it's all dependent upon sampling so we can finish on time, right? Well, we can do the same sort of thing for the application machine learning inference requests that are coming in, but do it at a much higher layer. But it requires working with you guys a little bit to understand like what is the equivalent of spatial random sampling for that request stream. And then if we can do that, then we'll be able to project. Now the errors in that case will probably be my 80% accurate in that case. This is more like 99% accurate, because here we can isolate for one subsystem, which is memory. And there's 6 or 7 different subsystems that are all being kind of wrapped in a container, and then we're monitoring the container. So we won't, because there's so many different distributions that we have to sample from, we may not be able to get as high accuracy, but we could probably get you 80% of the way. Would that, like 80%, does that scare you or
No,
okay?
We're not there, so it's...
Right, and the way to think about this is either on an A/B, blue, green, or a staging environment, where you push that and you fork some of your traffic to send it there. And if we can sniff on that traffic and control it and drop most of it, but keep some, as long as we can find for the traffic pattern that you have the equivalent of random spatial sampling for that traffic pattern, then the results of the overall system should scale up. Yeah. That's kind of our hammer, right?
Yeah.
Is sampling and then measuring. Okay. Thank you so much for attending my talk.